Union types are finally coming to C# 15 after years of waiting. The feature is a syntactic sugar at its core, but still union types come with a body of theory that you must understand if you want to use them effectively. Therefore, in this video, you will learn the underlying theory, and that is the theory that every programmer must learn one way or the other. No excuses. I will first show you the preview syntax of union types as it is now. I will then compare it with a nominal and anonymous sum types, both of which we can implement in C# already. That will make you see why the C# team has selected to develop the language in this way and not in some other way. That is very important to understand also. I will then show you how union types work under the hood. So if you stay with me until the end of this demonstration, you will not only learn the syntax, but also the powers and the limitations of union types and of the alternate approaches you might choose instead of them. So stay with me and see where that will lead us. The prerequisite to doing this demo is the use of .NET 11, which is currently in preview, and so I had to set the lang version option to preview. Another nuance is the global.json file, which pins the .NET SDK version for the entire solution. Without it, you run the risk of seeing ghost errors in the editor, where in fact the code is correct and the compiler would build it with no issues. So we are ready to start with demonstrating the new union type syntax. That will be the first and most important stage in this demo, which means that I will need your full attention to what comes now. We begin by defining a simple record type, cat, which just holds a name. And right next to it, a dog record, equally simple, also holding just a name. Then come the birds. We call them by the species. Now imagine yourself sitting at a porch and random animals come to see you. How would you treat them uniformly with no common base type and interface these types implement? That is precisely the problem addressed by the new union types. And here is where the magic begins. We declare a union type called animal, then simply list the three types to choose from: cat, dog and bird. That single line is everything the compiler needs to know. An animal is one of these three and nothing else. This nothing else is the key ingredient here, as you will see in just a minute. The result is that now we can collect objects of various types in an array of animals, just like we would do with any set of polymorphic types. I got visits from my dear cat Luna, a grey crow from the tree, the neighbor's dog, and my other cat Gilles the tomcat. He comes by other names too, real felon always on the run. Nothing can stop me from printing out a nice report where each line depends on two strings defined on a different type, not the one defined on the union type. Spoiler alert, the union type might not even exist. It is the implementation detail of the compiler how it will handle the union. But that's not where the story ends. What if I wanted to use some strongly typed label on the union type, so not to depend on what each of the contained variants defines? That is fine, because union is still a type and you can freely add members directly on the union type itself. That is where I define a string label that applies uniformly across all variants. But how do we implement this property getter? The answer is a switch expression on this. Each variant gets its own arm and we just pull out the relevant field from the concrete type. Even though each variant exposes a different member, we are able to unify them into one result that is common to all of them. But there is a caveat. The compile time warning indicates that we are missing a catch-all arm that can only throw an exception. Well, that is a glitch which you may experience while union types are still in preview. Once union types become official, both the compiler and the editor will know that we have handled all possible variants, and warnings of this kind will not appear. But the story does not end here. This animal type looks like an abstract base of the hierarchy of types. That is about to change now. I will define a second union type. I'll call it tag data. I plan to do something that cannot be done using inheritance. A union of integer, string, and boolean. The union acts like a base type, but it is not. It is all syntactic sugar. You will see that when I add a method to the union. Now observe, this method will appear on integer, string, and boolean completely uniformly, but only if they are assigned to a tag data variable. The method body is again a switch expression over the three possible types. An integer will represent the animal's age, a string will describe what the animal is bringing, and a boolean will be entirely about cats. I will repeat that the warning on the switch expression is still a false positive. It will disappear before union types become official. Exhaustiveness checking is precisely the safety net we expect from union types. And here comes the best part. I plan to collect both the animal and an accompanying tag data. You will now see me assign primitive types to the variable of union type, apparently with no conversion involved. And so my dearest female cat will come with a boolean flag false. There is no constructor call, nothing. Just assign a bool to a tag data variable. The rest is compiler magic. My favorite grey crow will pickpocket from tourists and bring the loot to my home. I will assign a plain string to a tag data object. My neighbor's dog is 6 years old and my favorite orange cat will do what he does best. The bool will tell the whole story. Now I can put both pieces together in the projection. It almost looks like I have called the toLabel method straight on primitive types, but it was the union type that declares this method and then does type matching on a boxed object it contains. If I run this demo, you will see the output that perfectly matches the objects I have created. All the labels are formatted as expected, and yet every label is the result of operating on an object of a different underlying type. That is the power of union types. In the rest of the video, I will show you how the world operates without the union types syntax. That is possible, and that will also help you better appreciate what union types are bringing to the table. But before we get to that demonstration, let me steal a moment of your time to remind you that this channel and everything on this channel is free, but only thanks to patrons, the sponsors who are sponsoring this channel on my Patreon page. So if you like what you have learned from this video and from other videos on my channel, then please consider joining the growing community of patrons on my Patreon page. There is the link in the description. As a patron, you will get the source code from this video and all other videos, and you will also get access to some discounts I occasionally post on Patreon. Thank you very much. Now let's get back to our code, because I plan to implement this same demonstration, but without the use of union types that are still not present in C#, they are coming in C# 15. I plan to develop one nominal sum type, and you will see what that means. We would still have the same three variants as before, each carries its own data, but then the question is, how do we bundle them into one unified type? One traditional approach is to introduce an abstract base record. Then make each of the concrete variants a sealed subclass of this abstract base. That is how we utilize inheritance to ensure that all individual variants are assignable to the same abstract variable. We can still define members on the base type. The awkward part is that this base record knows all of its inheritors. But the same compile time warning is this time a correct one. There is no guarantee that someone else hasn't introduced yet another subtype, just for fun. Let's send a friendly message to whoever did that. Lesson learned: inheritance does not guarantee a closed set of types, and the compiler cannot complete the exhaustiveness checking. That is what union types will solve for us. The lacking of the next fundamental ability of union types becomes apparent when we try to model a type that can be any of a few primitive types or other pre-existing types. We must wrap each of those into an explicit record deriving from the abstract base. That is why this structure is called a nominal sum type. Each discrete type comes by a name, so we call this a nominal sum. We can make our life a tad easier, like defining conversion operators for assignment. But don't get carried away. These helpers can easily make your code harder to read rather than cleaner. Nevertheless, adding members at the parent type is as easy as it ever was, with the repeated note that there is no exhaustiveness check here, and any type analysis must include a catch-all arm that will hopefully never be executed. The good news is that you can use nominal sum types the same way as the union types. I have literally copied and pasted the demo code from union types. Until the time union types come full to C#, my suggestion to you is to use this syntax in your code. Many of my followers asked me in the past why don't I use the one-off type, and here is the reason. I never believed that the C# syntax will go in that direction in the future, just as we see now it didn't. One-off is the anonymous sum type. That is the next demonstration I will show you. This type would capture an object of one of three distinct types. We call it the anonymous sum type because there is no requirement to name the components. Whatever comes in will be stored in a non-nullable object variable. That may require boxing depending on the captured type. The rest is formality. Three constructors handle each of the three type parameters. A convenient match method accepts three functions, one matching each type parameter. The catch-all arm can never be reached. The constructor guards the types. This implementation assumes all generic type parameters are distinct types, so we can define conversion operators again just to simplify the assignments. That will make the usage sites much cleaner. Then come the concrete component types, a cat, a dog, and a bird. We don't have to define wrappers around int, string, and bool. Properties and methods on concrete sum types will come in form of extensions. Label is the property getter on the sum type of cat, dog, and bird. It delegates to match, and each branch procures the result in its own strongly typed way. Another extension block appears for the sum type holding either an int, a string, or a bool. Mapping is the same as it was in previous two demonstrations. And then comes the prize. Except for the declaration of variables, the rest of the code is the same as it was with union types, to the letter. There is no type checking, no casting, no branching. And that brings us to where we started, the union types. They are simple and self-documenting. A syntactic sugar with exhaustiveness checking. Precisely what other two attempts in this demo didn't have. So let's just unveil the mystery of how these union types work under the hood. This is the principal scheme, not the exact copy of what .NET and the C# compiler will do, but it will nicely show the working principle. You can imagine a simple wrapper around a plain object value. There's literally nothing here worth mentioning. The important stuff comes later when you start defining concrete variants. Each of these is assignable to the object inside the union record. Then come the concrete union types, which are mostly an illusion. The compiler might generate a type under the hood or might skip that entirely. It doesn't need the type to figure out how to compile the operations. Type testing code will be generated from your code, and the validity of types involved will be verified at compile time because the compiler has seen your declaration of the union type. I have added catch-all arms to switch expressions, but the compiler won't add them. It knows that such things cannot happen because it has already checked all the types in the union. The code you write will be augmented and reorganized during compilation to ensure all execution paths run as intended. This is all the union types in C#15 will ever do. I will run the application one more time, but you can already see what's coming. All four variants are displaying the same output, yet each variant is using a slightly different syntax. Yet the variant that uses union types is by far the simplest and cleanest. This is everything you need to do to implement custom union types that consist of your custom component classes or pre-existing types or primitive types or any mixture of those. You can use whatever you like and just put it into a union.